Good morning, good afternoon, or good evening, whatever the time may be when you're watching these notes. It is that time again, math time, my favorite time. Today we're going to be doing section 3.5, derivatives of trig functions. So we get to put together two of my most favorite things, calculus and trig. Yay! Alright, so here I got an information box for you showing you the 6 trig functions and the ddx in front of them, meaning we're going to find the derivative of each of those. So we're just going to fill out this box first, and then we're going to have some fun. Maybe. I don't know. I think it's fun. Okay, so what is the derivative of sine of x? The derivative of sine of x is cosine of x. Ooh, Wouldn't it be so cool if the derivative of cosine of x was sine of x? It's not, but it's close. It's negative sine of x. Okay. The rest of them, we're just going to fill out, and then we're going to derive the rest of them. Because, I could tell you just memorize these things, but you know me, hopefully. I would rather you know where they come from, because it's going to make it easier to memorize them, in my opinion. So what is the derivative of tangent of x? The derivative of tangent of x is secant squared x. Secant x times secant x. Well, sine and cosine are related, because they're, complementary to each other. So their derivatives are related as well. They're not perfect complements of one another, but you can see they're related. Well, in the same respect, tangent and cotangent are somewhat related. So since tangent has a derivative of secant squared, cotangent has a derivative of negative cosecant squared. So if you're good with patterns, at least that one will be a little bit easy to memorize. And I saved these two for last because they're kind of wacky. The derivative of cosecant x is negative cosecant x times cotangent x. Eek, I ran out of space. And the derivative of secant x is secant x times tangent x. All right, well, you know what? I got this lovely white space right here. I might as well fill it in with some kind of notes. Let's have a little fun with the derivative of sine of x. All right, so we know that the first derivative of sine is cosine. And the derivative of cosine is negative sine. What that means is the second derivative of sine is negative sine, because here's first derivative, and then if you find the derivative of the derivative, you found your second derivative, boom. Let's find the third derivative, meaning let's find the derivative of negative sine of x. Well, the negative on the front is a constant. It's -1. It just comes along for the ride. So it's literally going to be the derivative of sine of x with this -1 in front, which is negative cosine of x. And the fourth derivative of sine of x, which means the derivative of negative cosine x. Again, the negative is just a constant that comes along for the ride, so it would be the derivative of cosine of x times -1. But the derivative of cosine of x is negative sine of x. So negative sine of x times -1 is sine of x. As it turns out, sine of x is its own fourth derivative. It seems kind of poetic to me that a cyclic function, a periodic function, has a periodic pattern in its derivatives as well. It just kind of blows my mind. Like I said, big fat nerd, you've known this from day one, okay? It's never going to change. Alrighty, so these two are the only two that I'm going to ask that you 100% just memorize, because it's really not worth our time and energy to show you why they're true. It's just easier to just go ahead and commit it to memory. But the other 4 are tough to memorize. So what do? Why don't we derive them for ourselves using some knowledge that we've picked up in the last few notes? So let's find the derivative of tangent x without having memorized it. How do we do that, Mr. M? Why not do the quotient rule? If we call tangent x sine x over cosine x, then we can use the quotient rule. And again, like I said, we have to just use the derivative of sine x. We'll just have to use the derivative of cosine of x. So if u is sine of x and d, sorry, my wife just said something stupid, confused me. Where am I at? V. Okay, here we are. V is cosine of x. Then u prime is the derivative of sine x, which is cosine x. And v prime would be the derivative of cosine x, which is just negative sine of x. She's coming unglued. I'm going to pause I'm pausing the recording now. Okay, she promised me that she could control herself. Now we're going to get back to the mathematics. All right, anyway, we have u prime, v prime. Let's go ahead and fill out our quotient rule. You know what? I better write it down and be a good mathematician. We have u prime v minus ev prime all over v squared. Time to fill it out. So our derivative is u prime v minus u v prime all over v squared. Well, this is cosine squared, and these two negatives cancel each other out, so that gives me plus sine squared. So I have cosine squared x plus sine squared x all over cosine squared x. And there it is, folks, the Pythagorean identity. Cosine squared plus sine squared equals 1. And since 1 over cosine is secant, 1 over cosine squared is secant squared x. We have just derived the derivative, weird thing to say, of tangent of x. And we're going to do the exact same stuff for the other three. Not a single thing is going to change. We're going to use the quotient rule on every one of these. Okie dokie smoky? Okay. Here we go. Instead of saying cotangent x, let's say cosine x over sine x. And u is equal to cosine of x. She's chuckling again. I'm going to come unglued. And v is sine of x. U prime is the derivative of cosine x, which is negative sine x. Stop it. And v prime is cosine x. And now we just fill out our quotient rule, which I don't feel like writing again because there it is. So we have u prime v minus u v prime all over v squared. All right, so sine x times sine x is sine squared, but there's a minus in front of it. And cosine x times cosine x is cosine squared. And hopefully you realize that both of these things are negative, which means I can factor out a -1, which is going to give me, I don't know if I can fit it right there, so I'll bump down to the next line. It's going to give me -1 times the Pythagorean identity. So since I'm running out of space, we'll just do like this, because we know that that equals 1, and we get -1 over sine squared, which is negative cosecant squared x. Ta-da! Okay. Popping right along. Secant of x. Now, we could call this 1 over cosine x, which means we would have to use the derivative of cosine of x raised to the -1 power. But I feel like that was going to cause us a little bit of trouble because we're going to have to use the chain rule. And now that I've said the words chain rule, I don't think I've taught you that yet. I can't remember. Well, I don't know. I teach too many things. So what we're going to do is we're going to use the quotient rule. So I'm going to call this actually 1 over cosine x. And we're going to treat 1 as its own function. So u is equal to 1, and v is cosine x. Well, u prime is the derivative of a constant, which is very simple. It's 0. And v prime, derivative of cosine x, is negative sine x. So our quotient rule, since I can't see it anymore, u prime v minus u v prime all over v squared. There it is. Let's sharpen up this v. There we are. Let's fill it up. U prime. Well, you know what? It really doesn't matter what v equals because u prime is 0, but u prime v minus u v prime all over v squared. All right, well, this is clearly going away. Whee! And these two negative signs are going to cancel out. It's going to leave me with sine x over cosine squared x. But instead of saying cosine squared x, how would I say cosine x times cosine x? Because if I write it like this, I can split this up into sine x over cosine x times 1 over cosine x. And that is where we get tangent x, secant x. Ta-da! And we're going to do the exact same trick for cosecant x. Hopefully you're trying to beat me to these things because it's not magic anymore. See, d over dx of 1 over sine of x. Where u is equal to 1 again, but this time v is sine x, u prime is 0, v prime is cosine x. Can still see my quotient rule right there, so I'm just going to fill it out from there. Again, u prime is 0, so it really doesn't matter what v is, but, you know, good mathematician, I'm going to write it all. Minus u v prime. Ah, look, that's where that negative sign is coming from. All over v squared. Of course, that's gone again. And since I'm going to follow the exact same pattern as last time, I'm just going to go ahead and write it as two separate fractions. I'm going to write it as negative cosine x over sine x times 1 over sine x. That's where the sine squared is coming from. And cosine over sine is cotangent. So we have negative cotangent x times cosecant x. Ta-da! Of course, I know in my table up top, I have negative cosecant cotangent. Yeah, multiplication doesn't care about order, so no big deal. I didn't even realize this one's also the opposite of the way it is up top, but again, multiplication doesn't care about order, so no biggie. So now that we've spent time deriving the derivatives of 4 of the 6 trig functions, let's just go ahead and use them. And we're going to be using the product rule, the quotient rule some more, and then down below we're going to be doing tangents and normals. Okay. This is clearly a product rule, x squared times sine x. I'm going to write the product rule, u prime v plus uv prime, where u is equal to x squared and v is sine of x. And feel free to race ahead of me. U prime, drop the 2 down to the front, decrease the exponent by 1. V prime, we learned on the other side of this paper, is cosine x. So we just fill out our product rule. The derivative is u prime v plus u v prime. And I'm pretty sure that I didn't clean it up much. I didn't. I legitimately just dropped the parentheses. 2x sine x plus x squared cos x. And the reason why is because there's really not much you can do with it. There's no trig identities hiding anywhere because both sine and cosine have no exponent. I mean, if they had exponents, maybe we could do some identities, but it's really not worth it. There you go. It's finished. Done. That's it. Okay. This one, clearly a quotient rule. I feel like we got a lot of practice with the quotient rule on the last side of the paper, but whatever. There you go. U prime v minus uv prime all over v squared. This time u is cos x. V is 1 minus sine x. Okay. U prime. Sorry, I was looking at my notes to see if I was going to have to clean this up, and I am, because we're going to have some trig identities. So u prime is negative sine x, and v prime is, well, the derivative of this constant is 0. So what we're really talking about here is the derivative of negative sine of x. Well, the derivative of sine x is cosine x, and this negative comes along for the ride. Now we just fill it out. And I'm realizing that I'm going to run dangerously low on space here, so don't write large. U prime v minus u v prime all over v squared. And I tell you what, I'm not going to FOIL this out. We're just going to leave it like that. Now up top, I am going to distribute the negative sine x to the 1 and the negative sine x. And at the same time, I'm going to multiply cosine x, negative cosine x, and oh look, another negative sign, so that's going to be a plus. It says equals negative sine x, that's coming from there, plus sine squared x, and these two minuses make a plus cosine squared x. Hey look, the Pythagorean identity. Sine squared plus cosine squared equals 1. So instead of saying negative sine x plus 1, because all of this equals 1, instead of saying negative sine x plus 1, why don't I say 1 minus sine x? See if I write it like that. Hopefully you'll see that the top and bottom are the exact same thing, it's just that the bottom has a second one of them, which means the top of this fraction turns to a 1 while this exponent drops to a 1. So the derivative of cosine x over 1 minus sine x is 1 over 1 minus sine x. Impressive. Fun. Interesting. The derivative was actually simpler than the function itself. Neat. Okay. Moving on. Moved up too far. Here we go. Tangents and normals. It says find the equation of the lines that are tangent and normal to the function, below at x equals 2. At x equals 2. You know what? 2 is not one of our special values. So we're going to have to use our calculators. And you're going to want to put it into radian mode, not degrees. This isn't 2 degrees. Remember, unless it says degrees, unless you see a degree symbol, it's automatically a radian. So the first thing we would have to do is actually figure out what our y value is. So we can't use point slope form without a point, right? So we have to figure out what f of 2 is, because that's what y equals. F of 2 is tangent of 2 radians divided by 2, which happens to be about negative 1.093. So our coordinate is 2, comma, negative 1.093. Rest assured, in the homework, I'm sure I will be having you do some evaluation at special places. Okay? Okay. And now all we need to know is our derivative. Crud! Have to do the quotient rule again. U prime is tangent x. Whoops, excuse me. U is tangent x. V is x. At least the derivative of v is easy. V prime is just 1. U prime is secant squared x. And we fill out our quotient rule. U prime v minus uv prime all over v squared. You're going to be so sick and tired of hearing the words quotient rule. We've used it so many times already. All right, let's fill her out. F prime of x, which we're going to use to find our slope of our tangent and normal lines, is u prime v minus u v prime, which is just 1, all over v squared. And you just have to plug a 2 into this. So you plug in a 2 there, there, and there, and there. And I'm going to save you the trouble. F prime of 2 is, meaning, again, you said you asked yourself, and you know what? The TI-84 doesn't do secant. So you're legitimately going to have to figure out what is 1 divided by cosine of 2. Then you're going to have to square that number. Then you have to multiply it by 2. Then you're going to have to subtract tangent of 2. and then you're going to have to divide by 4. So you're going to have to go through it that way. Okay. Anyway, but when you do that, you're going to get a slope of 3.433. So our tangent slope is 3.433, and our perpendicular slope, or the slope of the normal, would be negative 1 over 3.433. Negative 1 over 3.433, which comes out to be negative 0.291. Barely fit it on the page. Whew. So the tangent line, and I'll just write T for tangent. Y minus y1 would actually be minus negative 1.093, so it's plus, equals m, 3.433, times x minus x1, which happens to be 2. There we go. And when you write the equation of the normal line, the only thing that changes is the slope. You use the perpendicular slope, so we're going to drop the negative 0.291 right there. And there's absolutely no reason to get that into slope-intercept form, because who cares, right? We weren't told to. Man, that bad handwriting. And the very last example of today's notes, this morning's notes, I have no clue what time it is right now for you, is second derivative of secant of x. It says find y double prime. Okay, well, y prime is on the front. Secant x, tangent x. Well, you can't see that. The derivative of secant x is secant x, tangent x. So in order to find y double prime, we're going to have to use, you guessed it, the product rule. U prime v plus u v prime. Where I'm gonna go this way for my u and my v and stuff like that. Where u is secant x, v is tangent x. U prime is the derivative of secant x, which is, well, right here, secant tangent. And the derivative of tangent happens to be secant squared. There's a lot of secants here, isn't there? Interesting. Let's see what we get. So we're going to fill out our product rule. U prime, secant x, tangent x, u prime v, which is secant squared, plus u v prime. I forgot my prime symbol. I made a mistake. And you didn't tell me? You're supposed to tell me when I make mistakes so I don't keep going. No, not you. Not you. My wife is chiming in. You hush up. You be quiet, woman. Anyway, u prime v, that's supposed to be a tangent. I swear I'm smart. U prime v plus u v prime. There we go. Luckily, I didn't get too far into this question. Equals, you're going to get secant x times tangent squared x plus secant cubed x. Are there some trig identities hiding in there somewhere? Maybe, but we don't need to dig for them. And that's all, folks. I hope you had fun. I hope you enjoyed it. And as always, if you need anything from me, please hit me up on Remind. I'm always available for Zooming, and I'll see you next time.